Okay, ready to go? How's it going? How's the ELF homework? Did you guys follow this epic failure over the weekend? We accidentally released the solution to the homework. No, you didn't, right? So only some, but so now we posted both files, like a real original question and solution. There is enough to read in this homework to just learn from just reading. Hey guys in the back there, so maybe you can stop talking. Thank you. Yeah, so and solutions are there too. So I ask you to try to solve it, like literally there you have to code like 10 lines of code to solve it, but you have to figure out those lines. When I was a student, again, your age, when I was doing my PhD, sometimes I literally coded like 2 or 3 lines a day. And you say, wow, the guy is really slow. It's like understanding what to code was the major issue. So yeah, and then next year we will change it to do something more meaningful. But anyway, so ELF is there. It's due next Tuesday. Quiz is there. I think it's due today, if I remember correctly. That's about it. Any questions about anything in the class? All good? Okay, cool. So let's go back to the page tables for a second, and hopefully if we go fast enough through them, we will start the next lecture, which is how the system boots and what happens after the power on. Just let me quickly remind you, like the process of address translation, which we were covering for the last week, right? So what was happening is that when like on Intel x86 machines, right, this is your translation scheme. Really, when you have an instruction, something like move, and you using some value inside the EX register, I don't know, whatever it is, OXF, something, ABC. This part of the address is becoming one of the two parts of something what is called the logical address, right? That's the input to the segmentation unit, right? And specifically, this part is this offset. Like two of these guys are called selector and offset are called logical address, right? And selector is effectively an index into the global descriptor. On Intel, it's not just the global descriptor table. You can create different descriptor tables. I only teach global just to simplify things. So just stick with me, like don't bother about anything else for a second. And then like these two things go as an input into the segmentation unit. Segmentation unit does the check of the limit and adds the base, checks the permissions like read write, other things, whether you have even access right to this segment, and outputs a linear address, right? So that's the terminology. This is the linear address. This linear address goes into the paging unit and walks the page table. And at the end, we have a physical address, and this physical address is this number, whatever. It can be completely different from this one. It can start from 0 or like be total 0 together if you like however you configure the system goes to the DRAM, and like from here the value is fetched, and it's like goes on a memory bus, and if you load it inside the EBX register, the value will be placed inside the EBX register, right? Just a reminder. And we talked a lot about it, and this is part of the quiz today, right? So this is how it works. So you start with the logical address, as I just said, these two parts. One of them is an index in the, let's say, global descriptor table. Another is an offset. You do this base address plus the offset computation here, this plus. You get the linear address within the segment, hopefully, right? And that the entire thing is called linear address space. And that becomes an input into the paging unit, right? So this is the boundary between the segmentation and paging here, right? And what happens is that then we take the top 10 bits of the address here, go into the page directory, locate the pointer to the page table, take middle 10 bits of the address, figure out the index into this table and into the page table, locate the entry, and this entry will contain the pointer to the physical address of the page, and this lower 12 bits will be an offset within the page, right? So we all understand it. Question?
clarify, is there one single descriptor table on the entire system, or are there multiple GDPs per process?
Well, again, it can be different. So logically, and again, like, let me step back. What the hardware knows, the hardware just keeps track of global descriptor table register. So the operating system loads or can load a value there, which means that at this point you can have choices. When you build your operating system, you can make a choice. When you context switch between the processes, you can load a different value and like switch between different GDTs, right? And everything changes like instantly, right? And all the segmentation, like how you translate all the addresses immediately change. And you say, look, if it's a practical choice for whatever reason, you're building an operating system, maybe you don't have the paging unit altogether. Maybe the hardware is limited. You somehow convinced Intel to give you a chip without paging, or you didn't enable paging for whatever reason. You say, look, that makes sense. So every time I will switch between the processes, I will switch the entire global descriptor table. However, as we will see later on x86, segmentation is not used that much, really. All the segments will be configured with the base of 0, and all the limits will be 4 gigs. So they will provide the access to the entire address space. And since you're adding whatever here, the base will be 0, you add 0 to the offset, it doesn't change anything. So it's almost like nothing, but it has to be there. And at this point, you ask yourself a question, do I have to really change between two radically different global descriptor tables every time I switch between the processes? And do I have to waste memory on keeping different global descriptor tables, one per process? And x86 makes a choice that no, you don't. And the only segment which x86 is using is something what is called task state segment. I will explain it later. Bear with me. It contains a pointer to the kernel stack, if someone knows what it means. And you say, look, instead of changing the global descriptor table register, I will just go into the table itself and change the pointer or the offset of the something what is called a task state segment. And on context switch, the only field which will be changing on x86 is this field, right? And Linux does something similar. So there is really no reason to switch between multiple global descriptor tables for commodity purposes. In different research scenarios and different like hyper-optimized scenarios, you might choose to make different choices. We'll talk more about it. And to a degree, again, like, how can I answer the question? Like I can tell you a couple of papers online which say, do not switch the global descriptor table, or like commodity systems don't switch the global table. And then I can find a couple of papers which do. It depends on what you're trying to build. If you're asking a question about commodity operating systems, this is probably a good answer to remember. Just one field in a global descriptor table will be changed. It will be a base of the task state segment. You will read the source code of x86, where you will read the source of a specific part of x86, which is responsible for context switching, and then you will remember. And if someone else like pushes you into the corner asking, but can you come up with a different scenario? By the end of this class, you might have an answer. Good. I mean, I don't know, it's confusing, I get it, but that's the reality of life. So people make different choices, often for performance. Any other questions? Same, if you ask me a similar question about the page table and you have CR3 register, which points to the root of the page table directory on modern operating systems, in 99.99 cases, we switch the page table when we switch between processes. I don't want to go into like different scenarios when you might not do it, but in most cases you do. So there will be one page table per process. Good question. So, and partially segmentation is there for legacy reasons. Intel, like again, when the hardware was wimpy and really like 16-bit address mode and everything, there was simply no paging unit, just segmentation. people, when we're like, it's kind of like what happens today with LLMs or something, right? Back then, systems were really immature. People didn't know how to design them. And they said segmentation seemed to be sufficient, right? And later on, people started talking about more flexible paging schemes, and they came up. CPU designers came up with the paging translation schemes. And then you say, and Intel was on board with that, and they said, okay, forget about it. We will, in fact, when we design our CPUs, the logic of this segmentation unit is so complicated that we want to get rid of it. And when they transitioned from the 32-bit machines to 64-bit machines, they deprecated the segmentation unit, and they effectively said, like, it's there for legacy reasons and compatibility reasons, but all the bases have to be 0. Wow, man, like, they kind of kills the segmentation, but not fully. And then later on, attackers come back and say, look, we're gonna hunt your credit cards and everything like that, and bank accounts and whatnot. And it turned out that if you want to provide fine-grained isolation within a process, for example, imagine you have an SSH library, which like implements a secure connection to a remote server. You say, wow, and at the same time, you downloaded a library, which is some logging library from some corner of the web, which is really good, but who knows what kind of security practices were followed when this library was developed. You say, look, I really want to run SSH in isolation, just because if there is a vulnerability in the logging library, which allows me to read the memory of the entire process, I will lose my private keys, right? And so people started thinking about how to provide fine-grained isolation within the process itself, within the address space. And it turns out, actually that switching the page table every time you switch between those isolation enclaves is too expensive. But it would be nice to have segmentation, because you could have switched just a segment, and it's really fast. But by then, segmentation is already gone. And RISC-V, for example, brings back the segmentation. Intel is still deciding what to do, stuff like that. So it didn't really go away. It's just that in commodity literature, if you open a book on operating systems, people will not concentrate on segmentation. But really, the books which will be written in the next 5, or like today and in the next 5 years, they will bring back those mechanisms and a range of other 5 or something, which will tell you how to. These 2 are not the only one on modern CPUs. That's what I'm trying to say. There are more. I don't even cover them, but they are designed to provide this fine-grained isolation. Remember, we talked about software fault isolation, WebAssembly, stuff like that. So WebAssembly can be radically optimized with segmentation. That's an interesting observation, because you don't need, instead of masking, you can enforce the segment, stuff like that. But it's gone, so it doesn't exist on 64-bit machines. So you can play different tricks. So that's the answer, I guess. Any other questions? But in reality of life, it kind of it always goes in some kind of spirals, and people come up with new solutions, try to deprecate the old ones. They make mistakes. They come up with another version 2 levels of those mechanisms. Now we're version whatever, 5 or 6 at this point. Okay, so we got this point. So we got the translation. So we remember what's going on. The first part is segmentation. Just remember that it's always there on Intel. You cannot enable even paging without segmentation. Then the second part is paging. The things which I wanted to talk about is a couple of interesting but very useful things which are useful. I can potentially leave it like that and just move on to the boot lecture and never talk about it again until we get back to configuring page tables. And x86 will almost use just this. But I wanted to talk a little bit more for you to understand what happens in real life on modern machines today. So the very first thing which I wanted to discuss is that even on 32-bit machines, x86 supports 2 sizes of pages. I mostly talked about 4 kilobyte pages, and I almost never mentioned 4 megabyte pages, but they exist. And it's kind of interesting optimization. So instead of having a radix tree of 2 levels, they just have, a tree of 1 level. They say that CR3 register will be pointing to a page of memory. This is the root of the page table. But instead of having pointers to other roots here, to the leaves of the tree, they just say, okay, look, this will be a physical address of a page, like in this example, points. It maps whatever, page one maybe to page one to physical address 0. And the size of this page, instead of 4 kilobytes, will be 4 megabytes. Or like whatever. If you carefully count, it will be like some power of 2, right? But it kind of like composes nicely because you say, look, if I split my entire address space, which is like 4 gigabytes, into the 4 megabyte chunks, if you divide by 4 megabyte, you will roughly get 1024 entries, right? And this is exactly how many entries you can fit into one physical page, which stores this table, right? So instead of like, remember we said that the second level of the tree will somehow map this address range of 4 megabytes in some fine-grained manner, like essentially arbitrary in the address space. They just said that this is mapped to a single 4 megabyte page, right? And it kind of simplifies everything. You don't need to even configure the second level of the tree. You just simply enable a flag saying that this page table, the pointer to the next level is a 4 megabyte page. And by the way, Intel allows you to mix those. So you can say, look, my page table, half of those pointers will have it depends on a flag. And this flag controls the page size. It's either points to the level 2 or it directly points to the page, right? Got this idea? It allows you to create flexible address spaces, which mix 4 kilobyte and 4 megabyte pages. Got it? So x86 will use a 4 megabyte page table when it boots because it only needs 2 regions of continuous memory, and it's easier to configure. Although it's not like a showstopper. If you like, I keep asking on the exam, can you replace this 4 megabyte page with a collection of 4 kilobyte pages? It's not hard to build. And if you dig through the Git repo of x86, you will find the original 4 kilobyte page table. Clear? Of course, very next, like this is the Intel, like again, I keep showing those screenshots from the Intel developer manual. This is how the translation works. Again, we have linear address. Since the page now is 4 megabyte, the offset now is 22 bits, right? And only the top 10 bits are used to index into the page table or into the page directory specifically. It's just one page, not a tree really, just one level. Control register 3 contains a pointer to the root of the tree. And this is what I wanted to say. So the page size bit is set to 1, which means that, okay, this entry in a page table points to the physical page. And they are 4 megabyte aligned, so we need even less bits here. Instead of 20, we use 18. Not exactly sure why 18 instead of more, but instead of like, I would say 10, no, probably 18 is the right arithmetic. You can think about it and figure out why I'm wrong. Does it make sense? 4 megabyte pages. The next question, okay, what happens on 64-bit mode? Because for this 64-bit mode, like the physical addresses are much larger. Modern machines up to like 5 years ago, you allowed only like virtual addresses of 48 bits, and now 52 bits are allowed. And essentially, instead of 2 levels of a page table, we now use either 4 levels, or for this mode, it's a 5-level page table. And essentially, it's conceptually the same, but a couple of interesting things has changed. So first of all, those levels of the tree, they're still 4 kilobyte, or like specifically 496 bytes in size, right? But the entries are larger. So each entry, instead of being 32 bits, each entry is 64 bits, just because the physical offset. Remember, we used 20 bits in the original page in a 32-bit mode, but now we need more, right? And so instead of like fitting 1024 entries into each of these pages, you can only fit 512, just because if you do division 496 divided by 64, you will get 512, right? Okay, and so like everything changes a little slightly. So since you lost a bit, instead of 1024, you use 512. Now you use 10 bits of address. So essentially, each of these guys will point, like you take 9 bits of address. CR3 points to the root of the tree. You take the top 9 bits of address resolved into this level, still have names. So it's PML4E page I don't even know what it stands for. I know this was page directory entry. This one what's page table entry. What page directory page? Wow, good job. Like, oh, page directory pointer table. So okay, Intel bothered to give them real human readable names on 4-level page table. On a 5th, I think they gave up. Maybe there is a name, but just people just call. At this point, people call it like level 1, level 2, level 4, level 3, sorry, and level 4. It's just okay. Anyone can remember. It's just 4, and if you have 5th one, it's level 5. And then forget about those names. I mean, you still see those in the source code, but it's like no one at this point can remember. But the same idea. So each level points to the next level. Again, we keep like 40 bits because on 64-bit machines, that's the offset into like into the 4 kilobyte aligned page, and so on and so on and so on. And then you end on a physical address, and the same offset. Offset here doesn't change because the page is still for 496 bytes. So you need 12 bits to offset within, to pick any byte within a page, right? Make sense? Just wanted to make sure that conceptually, if you understand 32-bit page tables, 64-bit page tables are the same. And the flags here are very, very similar. So I will discuss flags in a second. Good? Make sense? Okay, now, since we talked a lot about the page tables and everything, and we kind of had this high-level picture of why they're useful and everything, if I ask you a question, what are the advantages of page tables versus segmentation? Again, if I start on it, it will be a lengthy discussion because there are so many, again, performance kind of trade-offs here that it will take us some time, but I don't want to go into this. But at a high level, what page tables are used in commodity operating systems like Linux and x86 as well are the following. So page table allows you to protect parts of the program. So for example, it kind of makes sense to map the text section or the code section of the program as read-only to disable code modification attacks when attacker just overwrites the code of the program, just simply has a straight move instruction where you, like, for example, you had an array, you forgot to check the bounds, attacker uses some extra large index into the array and writes the code section. And so, okay, it makes sense. So how do we do this? We have a read-write bits in this page table directory and page table entry. So page table directory in this naming scheme, it will be L1, L2, and this will be L1. So just be more specific. So for example, this is a page directory entry. If the page size is 0, it means that the next level of translation is present. Remember, it's not a 4 kilobyte page. And so these are the flags. So essentially, what we do here is we say, look, we use 20 bits of address to essentially as a pointer to the next level, right? And then we have some flags. And just to make sure that everyone is quickly awake, let's quickly do a poll here. So I will ask a couple of, because I'm falling asleep, yeah. Today's kind of a sleepy day, to be honest. I had my coffee, don't you worry. Where is my link to the poll? So something along those lines, right? And I will enable it. But we will quickly try to recover from this falling asleep situation. Let's start with this one. So the question I'm asking, why the 20 bits are sufficient in this case? Let me just maybe quickly copy this URL. I forgot to copy it and put it on the other page. It's a free response question. We'll do this. Let's see. Today I'm really falling asleep and I'm not sure why, to be honest. So I was asking this question here, right? So let's this URL here. Let's take a look at what is that we have here on the not using the extra bits. Well, but you should probably tell me why is that we don't have to use extra bits. Too many page frames. Address space is enough to fit the program. Man, really? By the way, so those the exams will be kind of specific. You know, the exams, just an insight into the exams. First of all, I mean, like, okay, let's finish the poll. But I will show you a link to the previous exams. I post them online. There is no secret in what we're asking on the exams. And exams will be on Gradescope just to save the planet and don't print like 130 copies of the 10-page document. But the questions will be free form, but they will be graded in a very, like, we will be grading on understanding. So you cannot just like make up some phrase and put there and claim the points for the answer. So I'll show you good answers and bad. So like maybe I missed, but yeah, this is the answer. The pages are always aligned to 4 kilobyte. So that's why the lowest 12 bits are always 0, so you don't have to keep them around, right? So this is exactly what I'm asking here. Is that clear to everyone, right? Since it's a free form, and I will anyone give you guys like all the points for this question, right? Let's quickly go back to this. Sorry, what is that I'm doing here? To this slide and take a look here. So do we agree with this? Do we understand that like if you have a pointer here, which points to the next level of translation, the convention is that this page is always to be more specific, 496 bytes aligned, right? Which no matter what value of this pointer is, the lowest 12 bits will be always zeros, right? It's a very simple concept, right? You just save this space, and that's why you use this space specifically for like keeping the flags. And let me explain very quickly what flags are there. So I'll stop the poll. Everyone in the class answered. Anyone need helps or need time? Sorry. Everyone is awake. Not me, not you. I know, tough. Where is it? Where is my wonderful slide, which I have to stop? I already lost it because, yeah, here. Okay, so but that's essentially the idea. By the way, don't hide poll everywhere. I actually have the next activity for you. So if we go here and I ask the next question in a second. Remember, what we're trying to do right now is the following. We're trying to figure out how to map the code of the program as read-only. So I mentioned those bits, like I said, that, okay, those specific 12 bits are free for the CPU to use. And some of those are unused right now on Intel, right? So they are ignored, or like Intel in later versions may be using those, but in this version, which I'm showing on right now on the screen, those bits are not used. But this bit, which is sits here, read write, controls whether the page is readable or writable, right? So it's a very useful bit here. It's a bit number 1. And if I ask you a question like, okay, bit number 1, read writes are allowed. My next question, actually, what am I asking here? Let me just today I forgot what is that I'm asking a poll everywhere. Let me quickly cross-check what my next question. Okay, I got it. Yeah. We'll ask it later. So if I ask you a question, so like this bit here specifically controls what range of addresses? It's a good exam question. So it's a page directory entry. So which means that if you look at the translation, the hardware just looked at the CR3, loaded the page directory, used those 10 bits, and is looking at this entry. And imagine it's a read-only. what is read-only? What is specifically read-only, you think? It's a guessing question, so you don't know the answer, but you can try to guess. Inside which page? You mean like this page is read-only?
Whatever.
I guess I guess that you're guessing correctly. You're saying that it's not really a page at this point, but because really we are translating 4 kilobyte pages because this page size bit set to 0, right? So, but any address with those other bits, so no matter what other bits are here, so like those access can be either ones or zeros, right? Any of those addresses are read-only, right? You're right. So it's kind of like the hardware blindly follows the translation mechanism, and you can kind of, like, as we will see in a second, the second level also has a read-only or writable flag, but you can terminate it early. If you say that the entire, just to make sure that those addresses, they control, it's like the range of those addresses is 4 megabytes. Entire 4 megabytes are mapped as read-only. Sometimes it's faster to terminate, because if you have a large code section, like, and it covers the entire 4 megabytes of memory, you say, look, all 4 megabytes will be read-only, and instead of like forcing the, like making sure that each page is mapped as read-only in level, in this page table level, you just map it once and set the bit here. So it controls the entire 4 megabytes, right? And the same will be like, the same will be in other scenarios when those other bits will be, will control like executable, other things like privileges and stuff like that. We'll see it later how x86 does it, but although they do it, actually, I don't think they ever they duplicate those bits in 2 levels, maybe for simplicity, but it's a nice exercise to try to see how you can optimize. Okay, good. This is clear, right? Okay, so we know that we can use those bits to map pages as read-only. What else can we do? So this is the explanation that the entire thing controls a region of 4 megabytes, and that's how we arrive to it. So it's 496 multiplied by 1024 gives us 4 megabytes. We can also control, and we will see it later, this bit, user or supervisor, is a bit number 2, which controls whether the kernel or the user level code can access the page. And the same rules apply. So essentially at both levels, you have this option, although I'm talking right now, it's page directory entry, but the page table entry has the same bit. You can control whether a specific page is accessible only by the kernel or is allowed to be accessed by the user code as well. And we will talk about it in detail. So just giving you a heads up that this bit exists. Question?
If there's
no, the hardware will blindly follow the translation. And if the translation terminates at the level of the page directory entry, you immediately get an exception. If you go level down and there is like a bit set, the operating system controls those bits, right? So like, yeah. And that actually, it's not like an error. It may be a semantic error. Maybe it's not what you meant to do. But if you have small code sections, obviously not the entire 4 megabytes read-only, but only a couple of pages which map whatever your 8 kilobytes of the code section are read-only. Right? So we will see. I just wanted to make sure that we understand the mechanics of how it works. So we'll come back to it, and we'll talk a lot about those privilege levels and everything, so you will understand everything. But just make sure that you understand that there is one bit which controls it. For example, if you want to see the working set of a program, meaning you load it like a giant piece of whatever, like it's a web browser maybe, or maybe like a text editor like Microsoft Word Office or something, and you say, but really, how much memory it is using on it? Mechanisms which CPUs provide right now, but the original one was this one. Essentially, in this second level of translation, page table end, bit, which is bit number 5, and the hardware sets this bit when the translation goes through this entry, meaning that the specific page was accessed. And the operating system can periodically scan the page table, reset those bits to zeros, and then scan again later and see that some bits are set. And this was the active working set of the program. And if you balance how often you reset and monitor those bits, you will kind of get an estimate of what the working set of a program is. And also it will help you if you do actively try to save memory, you can decide that certain pages which maybe were used in the past were not used more recently, and you can put them to disk. So this is how the swapping algorithm determines which pages go to disk, right? So you just to keep track of what pages were actually updated. And it's used in virtual machine migration. And again, Intel kind of rolled in other features, which I'm not covering in this class, because they were trying to optimize this tracking of this dirty working set, dirty pages. And the reason is that in virtual machine migration, the idea is that the user perceives only a minimal downtime. So for example, if you're playing Quake and your virtual machine in a cloud is migrated from one server to another, you might see like a 30 millisecond delay. Might be a huge deal for you if you're like a competitive gamer in a specific moment of time in a game. But 30 milliseconds, if you think about it, that you're moving the whole machine, virtual machine from one server to another is a very small downtime. And the way it's working is that if this is the entire memory of the VM, originally, like it keeps running on this machine 1, you just copy the entire memory on a second machine 2, and then you say, look, I did this iteration, and if I track the dirty pages in my second iteration, I will only copy over the dirty pages over, and I continue tracking it like continuously until I reach, like maybe I will do like 5 or 6 iterations. Typically 1 or 2 is enough, depending on the workload and what you're running. But at some point, the set of this dirty pages becomes so small that at this point you suspend the VM. This is where you perceive it, the human, you will perceive a downtime. Stop execution of the VM and move it to the second machine, and then resume on the second machine and keep running. But this iterative tracking of the dirty working set is a useful feature, right? And I mean, like we run stuff in the cloud. You will see it in your life later. And so there is this bit here, which is a dirty bit 6, which again, the hardware sets. So that when the page is mapped as writable, the hardware does a write. And when it goes through this translation entry, it just sets the bit. And operating system can periodically monitor those bits, resetting them to zeros to make sure that it knows which pages were written. Any questions about it? Accessed and dirty. So kind of useful bits. What else? Probably most often the page tables are used for something what is called a copy and write memory, or a lightweight implementation of the fork function. Remember that the fork itself clones the address space. So if you say, I will invoke a fork function here, and it was a process 1, the operating system creates an identical clone of this address space. Essentially, inside the child, the fork returns what number? 0, right? Someone built the cell, and inside the parent, it returns a PID of this new process, like P2. And you say, look, but do I really have to like create a page table for this new process and essentially like allocate memory and copy everything over? And modern operating systems don't do this. Instead, what they do is that they say, look, we will create a page table which kind of effectively copies back to this original copy, like of the parent, but the pages are mapped as read-only. And then only when the child or the parent tries to write into the page, meaning that at this point, the divergence happens, right? At this point, the operating system says, okay, look, I detected that you're trying to write into this page. So at this point, I will create you a copy and update this pointer. And the pointer of the parent will keep pointing to this page. But now both of the pages will be writable, right? Agree? So it kind of optimizes the fork and everything. Question? Correct. Yeah. So, but in most scenarios, this is what you want, right? The child and the parent are identical. All the sections are mapped identical because that's what you want. And then maybe if you want to change the mappings, one of them has to like do things. Either you write into those sections, maybe you deallocate memory and then map everything. Maybe you allocate more. In modern operating systems, there are system calls which allows you to remap, like change the mappings from read-only to write. You can upgrade. All this is handled by this copy and write. But essentially, remember I was saying a couple of lectures ago that fork might not be the slowest thing ever, because with this copy and write optimization, implementation of a fork is actually quite efficient, because you only create kind of like a lightweight copy of the address space by creating a page table and then lazily kind of do this copy and write thing. On the other hand, if you're very, very paranoid and careful about your performance, copy and write might hurt you in some unpredictable manner, because you say, look, I expect that this hash table is mapped in memory, but it's somehow, it's not just like specifically fork, but it's also a map system call. So sometimes the operating systems allocate memory lazily, and you pay the price of those page faults later. And the price of lazy sometimes is higher than of the price of eager. If you say, I definitely will be using this memory, maybe do something eager. And maybe like there are ways to control how fork does it as well. Okay, how can we implement copy and write? A question. What's the implementation? What bits will we set in the page table? Oh man, it's a poll question, but I don't have a question for this. I can quickly create. No, like anyone. Let's wake up for a sec. The storm is coming. That's why I think I'll go skiing. Yeah, exactly. So how will you set them up specifically? Yeah, so you have to make sure that everything what was mapped writable in both parent and a child is mapped read-only. You also have to implement metadata structures in the kernel to keep track of what was originally read-only and what was read-write, right? What was writable, so you don't accidentally upgrade read-only pages to writable pages later on. But essentially, the idea is that you originally map everything as read-only bits in both parent and a child. And when one of them issues a write, you will get a page fault. We're going to talk about exceptions and implementation of page faults. The kernel receives the signal that that program tries to access a page, looks up the metadata, says, okay, yeah, this page was copied on write, so it's really writable. So it's not like a bug in a program. It really tries to write it to this page and then creates a clone of a page and updates the mappings to writable, right? So nothing really super complicated. Right, so it's eager versus lazy. And that's a great question. So and there is no single answer. Depending on what you're running, eager strategy might be more meaningful. If you really try to use this copy, like imagine your implementation is something like an Apache web server, which I think Apache was doing up to a certain point. I don't know if they do it now. And on every request or like on every new user connection, they clone the web server for security purposes to isolate execution, right? And they say, look, but we're not going to plan to exec from it, this Apache, because we really want to run 2 Apache web servers now. And at this point, eager probably is more appropriate because you know that everything will be used, or most of it will be used, right? And obviously the cost of like copying everything eagerly inside the kernel is lower than like later on servicing individual page faults, right? So but on the other hand, you say, well, but I don't really know how big this new session will be. Maybe a user will click login and then immediately forgets about it. And maybe again, lazy is back, it becomes a better strategy again, because you have to make a prediction, and that's what people are trying to do in most cases. But for example, when you first fork and then immediately exec, then you say, look, why would I copy the entire address space? There might be like 1 or 2 page accesses, maybe no writes, maybe there will be a write in the, maybe there are no writes really, maybe there's a couple of writes on the stack because you push something, invoke a couple of functions, and then immediately exec. So at this point, like lazy is a clear winner. But you're right, so there is no single answer here. But what's important is to be aware of those things and see that when you're running like imagine you're like in a database field and you say, look, I really want to control the performance of my database. You have to be careful. You have to understand what Linux will be doing underneath. And having those insights, I'm pretty sure you will be able to recover fast what Linux is up to. Although like Linux is a whole different beast. Okay, so that's cool. And finally, we have to come back to this idea. Like when I started talking about page tables, I think last Tuesday or last Thursday, someone immediately asked a question like, what will be the performance penalty of the page tables? Like clearly there is some, although we don't hear much about it, but there is some. So if I ask you a question right now, what do you think this performance penalty will be? Like how to think about it? I will switch back to this figure for a sec to provide an illustration. Good question. As compared to what? As compared to the world in which maybe there is just segmentation, or maybe there is even no segmentation, if you believe that there will be some performance penalty in segmentation as well. Like the addresses, imagine for a second, there is no segmentation, or segmentation is blazingly fast, which is kind of true in practice. And just compare between segmentation without paging, meaning the address from the register goes immediately to the memory bus, versus the page translation unit is enabled and you have to spend some time translating the address. How to even think about those numbers? So what is the overhead of page table? Correct, but can you give me the numbers? Imagine again, interview at your dream company and they ask you this question. So that might cut it, but not ideal. But you're right. The direction of thought is right. You
The two extra memory access, correct? You have access to page directories and page.
Right, exactly. So when you do a move instruction and you have something like you loading from address of the in the EAX value is this one. What are those two extra memory accesses? Who can tell me real quick? 2 is the correct answer, I think. 2 extra. Well, at this point, it's simple. So who can tell me? Where those 2 extra memory accesses are coming from? Oh, okay. Of course, you have to read this entry from the page directory to figure out the pointer to this entry, and you have to access this entry to figure out the pointer to the page, and then you do a load from this physical address, which goes into EBX register, right? Agree? So this is access number 1, and this is access number 2, right? Okay, good enough. Maybe good enough for not so good company, but like, what if you really want to crack the big good company or whatever the dream is? How many cycles? Extra cycles. Kind of. That's good, but not good for us. Can we give a better answer? You want to give us? Okay, that's better. Like we say, look, let's take a look at what can be in L1 cache. So definitely, like, how big is L1 cache to begin with? So do we know the number? I mentioned it a couple of times, but you really have to know these numbers by heart. I will make sure that we added them later to the quiz when we talk about the mem. What? 3 what? No, 3 cycles, agree. 2 to 3 cycles access to the L1 cache, but what is the size? Few tens of kilobytes. Okay. Anyone knows a more concrete number? 64. Oh man, I lost my pen. Like, meanwhile, okay, I'll give you time. The interviewer is friendly today. That's me. And they ask you, okay, guys, I'll give you a second chance. Can you look it up for me within like 5 minutes? Yeah, okay. That person is smart, so he started Googling. That's the way to go. Like, imagine, like, I'm not saying about the interviews, but in real life, you will have to Google. So, okay, my question right now is how to even Google this. Okay, where to go? So go ahead and Google. Maybe ChatGPT, maybe anything. If ChatGPT, make sure that it gives you a quote from where it comes. And raise your hand when you know the answer, and then we will like wait for enough people to figure it out. And do I have connection? No, raise your hand if you know the answer. And then I will show you how to. Okay, 1 person, 2, like 3. You need to know where to go for this information. Have a good. Man, you should we'll take a look. Okay. Next level of suffering, or not suffering, but the first step in this search. So what's the first step? If you're an Intel machine, I am on Mac, but let's for a second switch to Intel. What do we do first? We want to know the cache size of the CPU we're currently using. Okay, so okay, no, but the very first step. What's the first step? The very first step is figure out which CPU are we using right now, right? So how do we do this? What? LS CPU, something like that. I don't know if it runs on Mac. No, let's do a cell into shell at cs.uta.edu. Hopefully it will work. Or it will ask me some stupid, oh no, it doesn't. LS CPU, for example, and it will tell you a bunch of flags, but man, they're running AMD Epic. AMD Epic is good enough. So, but this is specifically the model of this CPU, right? So it's AMD Epic 7502, right? Man, you're smart. But I don't trust you. It also says hypervisor, other things. Like imagine like we want to double check. Maybe AMD does it. Intel may not. But you're right. So, but let's do this. We say this AMD CPUs. Actually, I don't really know the answer for AMD. I'm kind of like for Intel there is an ARC. Let's quickly switch to Intel because that's the thing which I'm frequently using. And how is it we can we will do this different server just to LS CPU, okay. Cat proc CPU on VSD, no, not even this. Don't have rights. Well, I'm confused now. How can we go about it? You're a better searcher than I am. I failed this interview. Okay, let's go with AMD. So Arc, Wiki, or something exists for Intel. And we will go into this. Wikichip is the good resource, probably the best which you can come up with. Like that's where I was going as well for Intel as well. And it says specifically for this CPU model, it will list you carefully L1 sizes, and it actually says that it says these two numbers, which match my understanding, but somehow we saw a different number. So right now, what I'm claiming from this wiki, and you have to more carefully read what those numbers mean, that L1s are it has 32 cores. It's a 32 core machine, I believe. Number of cores 32. Each core has a 32-bit data cache, this specifically instruction cache, and a data cache. So instruction and data caches are separate. There are the two different hardware structures. Each of those are 32 bits. And the total, if you multiply, maybe lead us to a total size of L1 cache on the whole socket, although each core can only use the 32 kilobytes. The total will be 1 megabyte. Agree with this? I mean, sorry for like this kind of detours. I don't see a lot of AMD CPUs, but the logic for Intel is the same. And what I meant to say is that this is how you look it up. You figure out the number of the CPU you're looking at, and then you go for this Wikichip, which is one of the most reliable sources of information on CPUs. So it's 32 kilobytes. That's what we wanted to get, right? So imagine you had some time to look it up. Maybe it's a take-home exam, or maybe it's like open book exam or something like that. So, okay, got it. So the first level cache is 32 kilobytes, right? Data cache, L1, 32 kilobytes. So this thing is a 4 kilobytes total. So most likely this entry is in the L1 cache, and this first access, extra memory access, takes us 2 to 3 cycles. Agree? What about the second access? How many cycles does this one take?
Would it not take a similar amount of cycles?
Will it? That's the good question. It can go either way. So if you say, do you have a theory?
Well, I guess what I'm assuming is if it's still in the L1 cache, then it would.
Yeah, if it's in L1 cache, it will take the same amount of cycles. The question is it in L1 cache or not? How can we think about it?
So L1 cache seems like, so like there's a fairly large chance it's not in L1 cache once you get to the page table.
Correct. And so but at this point, you have to build an argument like this. You say, depending on what is that I'm running and the working set of my program. So for example, if you're running like an infinite loop, which reads the same address over and over and over, then everything is cached, right? All these translation levels are cached. And then it's like 2 to 3 cycles. But if you're running a database join, which like uses almost all of a 4 gigabyte memory, then all of these, the entire page table tree is populated. The second level of this tree contains 1024 multiplied by 4 megabyte entries or 4 kilobyte entries. And the total is 4 megabytes, right? And so 4 megabytes clearly does not fit into L1 cache. Then which cache, where can we find it? Like, is it L2, L3, or do we spill to memory? Can someone build an argument here? Well, again, back to my wonderful, which if I don't, let me just quickly stop this, keep this thing. We go back to the same wiki page because we know that we kind of understand it. L2 says, okay, on this version of an AMD, there are 32 cores. Each of them uses half a megabyte of a cache. So the total is 16 megabyte, right? But again, like if you're accessing the hash table from a single core, then you know this core accesses the entire address space, right? Because you're running a hash table in parallel on all the cores, but they all access keys randomly, right? So probably it will not fit in this in the half of a megabyte of L2, right? We go down, we say like, how big is L3? L3 is shared, and it has, on this specific machine, AMD does those tricks. It says, okay, there are 8 16 megabyte caches. So, wow, without even concrete understanding of this, we probably know that it will be found in L3. So if it's in L3, then again, maybe this wiki will actually list you a latency of accessing the caches somewhere here, which would be nice. And they do, maybe for the generation of the CPU, not for a specific model, but let's assume for the simplicity of it that it's roughly 50 cycles, right? Let me come back to it. So this second access is, if we count it correctly, and we did it kind of rightish, takes roughly 50 cycles. And the access to memory itself is, if it's a hash table, nothing is cached, or maybe it's because the entire data set of the hash table is 4 gigabytes and the caches are 128. So probabilistically, this will be only like in 90% of the cases, this is real access to memory. So this is a 200 cycles or 250 cycles of memory access, right? So the total grew from 200 to roughly 252 cycles, right? So it's not like a second memory access, but it's some fraction of it. But you have to be careful about it, right? Question. Right, and they are also process specific.
Then like the
Correct. You're absolutely right. So if you're running 2 hash table or a hash table in a database join or something like that, then you also compete for those caches. And that should be part of your answer as well. But this is how to think about it. And this is again, my goal in this class, and I keep saying that it's just a goal in systems in general, is to say, look, you're executing this move instruction. Maybe it got compiled from some array access where you access an array of the hash table and you accessing not the key, but the hash of a key. And internally it's a move and someone asks you, okay, how long will it take? And you have to think about it and give an answer, right? And this is how to think about it. So question. Correct. So the instruction memory, by the way, on every move access, there is an instruction pointer which points to an instruction. It goes to the next instruction. And yes, it goes through the same segmentation and paging mechanisms. And only the L1 data cache is separate. And then the addresses are shared in the L2 and L3 caches. And you have to, again, typically programs are small, or at least the working sets of programs are small. And so it's rare to see a miss on the instruction. You can easily fix it early on in development and make sure that you don't. But typically hardware prefetchers and everything take care of it. And normally it's uncommon to see a miss on an instruction. So it's less of a problem, but you're correct. So if you want to really give concrete answer and someone whoever is interviewing you says, and you're jumping around in some random fashion through the memory, then this is also maybe a translation because your instruction pointer changes through some range and you say, I don't know how big this range is, stuff like that. Maybe you're using some, I don't know, some super tricky security defense. But yes, it's there to it. It's what's nice about your question is that you ask, do the instruction addresses go through the same translation mechanism? The answer is yes, they do. Is the what? No, the page directory is kind of like a data which is used by the CPU hardware internally. Yeah, that will be stored in a data cache. the actual instructions will be stored in L1 instruction cache. And but those entries will always be stored in the data caches. And there are some specific caches which I come about to talk in a second. But okay, do we understand at least, like, I'm not saying that, okay, we got the complete understanding, but this is the gist of how to reason about this performance. And it's really a problem. And that's one way to, like, I here later in my slides, I have this question asking, when do you want to disable paging? I think somewhere here, I forgot exactly. And this kind of exercise, which we did in a second, kind of steers you towards it. This is where the page tables are becoming a bottleneck, because instead of like paying a price of 200 cycles, it goes to something like 253 cycles, and or some other number depending on your workload, right? And so when someone asks you, like, where will you disable paging? So what will you answer? What kind of an application you're running? Correct. When your working set, not exactly the working set, but when the metadata of the page table tree does not fit in caches, right? So meaning that the working set of the program can be like large enough, but still the page table itself still fits, right? So it's a slightly different equation, because in a case of a 2-level page table, right, the whole page table is roughly 4 megabytes, right? So it, like, that's the working set, like, can be, in order to even achieve this size, the working set has to be like 4 gigabytes, right? So it's a slightly different things, right? So the set of the metadata of the tree versus the entire working set. Yeah, exactly, right. But what programs, what applications? If someone asks you like a straight question, like, give me an example of an application which has this working set. And also it has to be accessed in some random fashion. Because if I'm streaming a movie, my accesses are sequential, right? It's important to understand that if accesses are sequential, the hardware prefetchers will take care of it, and they're smart enough to prefetch everything. And of course, the prefetch itself will trigger the address resolution underneath, so the whole page table will be walked, and the whole page table will be kind of cached, and everything will be fine. So in addition to having the working set of larger than 4, like whatever, not fitting in caches, typically the accesses should be also random or semi-random. Because in the case of a sequential access, if I just simply streaming a movie or like going through the working set in order, then it's not a problem. So randomness is also important. So what is this application then? Database? The answer is yes, but do you know which part of the database actually does those random accesses? Did you guys take database classes? Not yet? Cool. Like you don't know how to build joins, right? So joins typically trigger either hash-based algorithms, like there's a hash table internally inside the join which triggers random accesses, or joins can be sort-based, which is also like kind of random access. So databases, yeah, good answer. What else? There was another hand I missed. Yeah, so hash tables and in-memory key value stores like memcached, stuff like that. Those are the ones. Metagenomic workloads also trigger a lot of like hash table, because you like counting k-mers or whatever, you're doing alignment and stuff like that. And after that, it's up to you. So maybe I should stop here. I don't really know other, but like think about them this way. And okay, cool. So just making sure we understand. Of course, CPU designers, they're not dumb, and they have like decades of like whatever. And they said, okay, guys, we understand it's a problem. We'll introduce a special cache on a CPU. It's called translation look-aside buffer. And every time we do a translation in this cache, we will remember where the virtual address maps to. They will remember those translations from virtual to physical and keep it around. So it's yet another layer of caching, right? So this cache is, again, if you took 3810 from Rajiv, he will tell you that, okay, it's done in parallel with the with the L1 lookup. So it's essentially within the same cycle, you look up the TLB. There is like some trick to make sure that it fits into one cycle, but typically like all the CPUs do it. And then, okay, typically you don't walk the page table. Then the previous question about the performance gets on steroids, like becomes on steroids. Like you have to keep this TLB in mind. And now you say, look, guys, I'm so good, but I graduated from University of Utah, very good school. Not kidding. And by the way, took a class from Professor Burtsev, and he's like he made us to sit for 5 more minutes after the class. But the thing is that you say, look, but do I even know how many TLB entries are there? And man, this week I should tell you, but it doesn't. And so you say, look, but I'm still smart enough. I will go to EPIC 7501, previous generation. Maybe this one will tell me the TLB size. Family EPIC. Family definitely will have the number of TLBs. No. On Intel, they always have. But essentially, there must be a description of the entire family with characterization of the entire generation. See also Milan. Okay, let's take a look at Milan. Maybe Milan is the entire family. What about here? TLB. Still no. But 64 TLB. Okay, how did you find it? What was the search? Good. So that's okay. I got stumbled, but my only comment here that verify the source. That if it's just some kind of a Stack Overflow answer, make sure that you find a PDF. Like in my experience with Intel, the Wiki chip will always list. So you said 64, right? It's not a huge number, right? And you maybe it doesn't even change your equation that much, right? So, but then those, yeah. So essentially, that's how you go about it. But on Intel and stuff like that, those numbers might be slightly larger, I would assume. But that's the way. And I will come back maybe like to make sure that like post us like something online to make sure that we understand that we know the size. But okay, this cache is in general, it's a huge like great improvement. So at least for I think the number is wrong, so it cannot be that low. I would say that on Intel it's in the order of 512 TLB entries, so it should be larger. What do you think? They only collide between processes, or they differ between processes only when you run 2 different processes and 2 different address spaces at the same time, right? But like the real answer here is that, again, think about how it works. The way it works is that when the pipeline tries to issue a move instruction, it needs to resolve the address from virtual to physical. Obviously, the CPU has a private pipeline. So in fact, if you have hyper-threading, then you will have kind of like not 2, but 1.5 pipelines because some parts are shared. So the TLB sits right next to this pipeline because you have to resolve the virtual to physical in the same cycle. So it's very close in terms of silicon as well. Great question. So did you guys all understand like if we have this cache, what happens when we switch from one process to another? Like for real. Because if we leave the cache dirty, the next process will be able to access the memory of a previous process, right? And in the past, the entire TLB, when you reload CR3 register, gets flushed for this very reason, which makes like it you take a performance penalty because the TLB is empty. You start walking the page tables, you warm up the TLB, then you run forward. But again, things got into not Intel, like all the architects are kind of like smart people, and they said, okay, by the way, guys, in order to avoid the flush, we will add a tag. It's called tag TLB. So there will be entry in this cache which remembers which process resolved or which process owns this entry. On Intel, this tag is called process context identifier, PCID. But in general, the whole concept is called tag TLBs. And then if two processes are running and you context switch, for each entry, you remember that this is like from process P1, and this one is for process P2, and you don't have to flash them on context switch, right? So that's how it runs today. By the way, for whatever reason, I think even up until now, Linux does not support tag TLBs. The management of correct TLB flashing is so complicated because Linux is so internally complex that they have a patch, they had it forever. I don't think they committed it really like or merged. I think Linux still doesn't use tag TLBs. So every time you context switch on Intel, you pay the price of flashing the TLBs. Good, so we got, this is important, TLBs, but you're right. And still the problem, if you are still within the same process and you change the memory mapping, maybe you allocated memory or deallocated memory, for example, you freed the memory. At this point, you have to flash the TLB, right? Because the stale entry will still allow you to access it. In the past, you really had to flash the whole TLB. Now there's a specific instruction which allows you to flash a specific entry. But this is where we are, right? And okay, so TLBs are important. We understand when we will disable paging. Just 2 more minutes and I'm done. Don't forget that real counting, if you are doing the interview question, the logic which I did for the 2-level page table, don't forget that like modern 64-bit machines run 4-level page tables or 5-level page tables, and you have to do the counting for whether it's in L1, L2, and anywhere else for each of the levels. But the logic of the counting is the same. So please go ahead and impress your interviewers, get those jobs, stuff like that. And essentially, one final thing before you all like start meeting. I said that I keep asking this question, why will you disable paging? We figured it out. We said, okay, we're running the page tables, databases, hash tables. In practice, operating systems do not allow you to disable page tables. There are tricks you can do it, but in practice, it's not the answer. What is the answer then? Tell me. What's the practical solution for this problem? Mapping big pages, so super pages. So on 32-bit machines, instead of using 4 kilobyte pages, you switch to 4 megabyte pages. On 64-bit machines, the sizes, the supported sizes will be 4 kilobyte, 2 megabytes, and 1 gigabyte. So you say, I will load my database and I will use 4 gigabyte pages. Linux supports it, all major operating systems supports. 2 megabyte pages are supported transparently. You don't even have to change the code. If you want to load something with 1 gigabyte pages, you have to allocate memory explicitly from that region on Linux, at least like as of 2 years ago. And that's the answer. And then, like, again, the counting changes because you say, look, I erased, if you erase one level of, it's 2 megabytes, erase 2 level is 1 gigabyte pages, and only these two have to fit in caches and stuff. So make sure that you're counting correctly. So super pages are the answer. Okay, so that's probably everything I wanted to talk about today. You probably know enough about page tables, and I will come back and start on system boot on Thursday. So essentially what happens when the machine is powered on and stuff like that.